In this video, we'll try to explore the behind scenes of crafting GPT. GPT is a large language model built on top of transformer architecture, which solves a problem we used to have with the recurrent neural networks and LSTMs, that is processing data in parallel and understanding the context in long text. We'll see the individual steps that involve in GPT making, pre-training, which is a crucial step where LLMs learn patterns and knowledge from the internet scale data. Anyone who wants to train the LLM will extract the data from internet, which is huge, and expects the LLM to predict the next word based on the context given to it, which runs over multiple hundreds of epochs and expects the LLM to grasp the knowledge and understand the patterns. And in the next step, which could be RLHF or it could be fine tuning, depends on the use case. But if we want to do the RLHF, we are trying to align the model with the human preferences. For every prediction that LLM generates, we'll use the reward model to give the feedback to the model and learn from its mistakes, so that it will more align to the human preferences. That is, it will try to give possibly helpful text and honest and safe responses. Simple step that we perform after pre-training or RLHF, where we expect our LLM to shine on some task-specific data. As a result, our model becomes proficient at some applications on data which it is trained on. Uh, yeah, that's all fine tuning is. But in this video, we'll concentrate on pre-training and RLHF at GPT-2 scale and see the script that involves in simulating the GPT-2 training and RLHF. Exploring the pre-training script that we're having here. I'm using weights and bars to track the training script, pre-training here. I set up the device with CUDA if I'm using GPU or CPU here. Obviously, I'm using GPU in this case because I take the GPU instances from Lambda, which charges based on our usage. And then I'm setting up the GPT-2 configuration with this vocabulary size and positions 512, which is the context window length. And embedding dimension set was set to 384, and I'm using 6 transformer layers. And number of heads is set to 6, which is multi-headed attention. If we look at the architecture of transformer, which uses scaled dot product attention in multi-headed to gain the different aspects of context, to learn the different aspects of context technically. We are setting that to 6 and using the model and tokenizer from GPT-2, which are available from the transformers library. And I'm creating a small data set as we already discussed. We're trying to simulate the environment of GPT-2 training. And I'm using wiki text, taking the 10,000 samples, which are of minimum length 50, and created a torch data set here. And then using the data loader from the torch and as well. And I'm setting the number of epochs to 15, which is obviously not even 1/10 of the actual number of epochs that happens in real scenario. But yeah, this is for just learning purpose, so I kept it to 15, which costs us less, and number of warming steps to the 10th of actual training steps. This is used by a linear schedule with warm up. This is scheduler for learning rate, for calculating the learning rate at each epoch. I'm using Adam optimizer with character weight decay and setting the learning rate to minimal initially, and then grows with until warm up steps is reached, and then decreases gradually. This helps us in learning initially faster and then stably learning after that warm up steps completed or warm up steps is attained. And then I'm using the model or train initially in training mode, going to each and every epoch and calculating the loss at every step and back propagating the loss and adjusting the optimizer and scheduler, which is learning rate, and logging the loss, batch loss, and learning rate at each step, at each epoch, technically, which can be seen from weights and bias here in our case, and then finally saving the model at each checkpoint as well. And once everything is completed, I'm saving the model here, which will be used in RL step next we are going to perform. I'll also explore the RLHF script. Here also it's simple. If I'm using WNB again, loading the model which was saved from initial pre-training step, and using the same tokenizer which we earlier had, and keeping the learning rate and number of episodes to minimal here. Maximum steps is also 50 and temperature was set to zero point 0.7, which controls the randomness of generation, which can be, if we keep it lower we'll get the deterministic results, and if we keep it higher we'll get the random results and more creative sometimes. And yeah, learning rate is also kept to minimal initially. And uh, Adam optimizer has been used here, and such technique. We are using 1,000 episodes, starting with the simple prompt. Once upon a time, it will start generating the story, and we'll check the sentiment and reinforce based on the sentiment. In reinforcement function, we are keeping it to model train environment, and this generate text will generate the text using the prompt it is seeing, and generate the sentiment based on the generated text. This is human feedback in real life, but we are using the text blob package to give us the sentiment for this text. Once we have the text, what we are doing is technically using the sentiment to reward to avoid a reward for our model. That is, we scale the loss based on the reward and back propagate this loss, and keep the optimizer and uh, learning state, and I'll keep doing this for these 1,000 episodes, so that it only tries to give the positive story, don't go in a negative way. That's reinforcement learning overall. Spinning up the GPU instance, which costs us 0.75 per an hour. Uh, I'm selecting California here. This is the GPT file system that I initially created, and I'm launching the instance. Uh, into the instance that I got from the Lambda cloud. It's now completed booting, and now I can use it. I now did the research, and yeah, I'm here now. So this is the pre-transcript that we earlier explored. I kept it running. I have an account. I'm selecting the second option, pasting the key that I already having. So it was generated. A run was generated. You can basically click on this run and go see over there. Ran for 15 epochs, and the loss settled at 1.1 in our case. Again, this is just 45 parameter model, and the loss we got is very reasonable. We could have kept for 15 more epochs and expect this to go a little behind 0 0.7 or something. And but yeah, this took me about 3 hours to complete. So based on that, if we kept for a few more hours, our loss would have been much better and could generate the reasonable text. But since this is just for a learning purpose, I kept it very simple, and we can see the detailed batch loss. How is it changing for over each epoch and each step here in WNB. But yeah, since we ran it for a very small number of epochs, this might not definitely overfit. But yeah, if we could run it for a little more epochs, at least to the 50, I would say, the text that our model can generate would be much more reasonable. All this is for just learning purpose and simulating the environment that we'll be seeing for GPT training. And again, the RLHF, I kept that script running as well. Uh, the RLHF training script that we earlier seen. This is also performed, I would say, reasonably initially, and then keep on generating junk or some kind of a, because the reward model is static. It is not learning at all in our case. It's just a simple sentiment emitting function using the text block package. Uh, so it's just emitting the same kind of reward every time, and the model tries to avoid the negative words over the time, but it kept generating the junk after a few episodes, I would say. So maybe we should have reduced the episodes or keep the neural network for reward model, and some kind of DPO or PPO, proximal policy optimization or direct policy optimization for adjusting the policy for that reward model. Yeah, again, it's just a simulation. So this just worked out, and this is how the training happens for GPT. Uh, yeah, that's all for this video. Thank you.